All right, and welcome to the first lecture in the sequence of Chapter 22, which will cover collectively gluconeogenesis, glycogen metabolism, and pentose phosphate pathway in metabolism. So this lecture is just going to cover gluconeogenesis and the regulation of gluconeogenesis. And let's go and start out with what is gluconeogenesis? So, and specifically, how does it operate? Well, the ability to synthesize glucose from common metabolites is incredibly important to nearly all organisms. In human metabolism, for example, we consume, it's variable, but between 160 to 200 grams of glucose per day in a standard diet, and about 75% of this is going to be used in the brain as part of resting metabolism specifically. So body fluids carry about 20 grams of free glucose at any one time, and our glycogen stores normally provide an additional 200 grams of free glucose on demand from muscle and liver tissue specifically. So the body therefore carries just barely more than a day's supply of glucose. And if you're not obtaining glucose in the diet, the body has to have some mechanism for synthesizing glucose from precursor molecules. The name of this synthesis, de novo synthesis of glucose, or the production of glucose from metabolites, is called gluconeogenesis, which means literally the generation of glucose. So in addition to the necessity of being able to synthesize glucose for neuronal function, muscles consume enormous amounts of glucose via glycolysis, which therefore produces large quantities of pyruvate. And if you're undergoing periods of vigorous exercise, muscle cells can become anaerobic, and pyruvate is going to be converted to lactate. So gluconeogenesis actually provides a mechanism which salvages this pyruvate and lactate and reconverts it to glucose. So in summary, we have a couple roles. We have neuronal function, because you must have blood glucose for neuronal function, unless you modify your metabolism under long periods of very low carbohydrate dietary restriction. But that's something that's outside the spectrum of what we're discussing right now. And then we also have for recapturing pyruvate and lactate. Following anaerobic metabolism. So what we're going to be talking about in a few lectures peripheral to this is another pathway of glucose metabolism. The pentose phosphate pathway is a primary source of NADPH, which is the reduced coenzyme essential for most reductive biosynthetic pathways, specifically lipid biosynthesis. And like I said, we'll be talking about that in a following lecture, but just start off with gluconeogenesis. So note that substrates of gluconeogenesis include pyruvate, lactate, and amino acids as well. So in addition to pyruvate and lactate, other non-carbohydrate precursors can be used as substrates for gluconeogenesis in animals. And these include most of the amino acids, as well as glycerol and all of the TCA cycle intermediates. So on the other hand, fatty acids are not substrates for gluconeogenesis in animals, because most fatty acids yield only acetyl-CoA upon degradation, and animals can't carry out the net synthesis of sugars from acetyl-CoA. Interestingly, lysine and leucine are the only amino acids that are not substrates for gluconeogenesis from the pool of amino acids. So note that as a substrate, substrates include pyruvate and lactate classically. Plus amino acids. So tying back to our discussion about metabolism as a whole and how all the systems feed into central metabolism, breaking down large-scale macromolecules to constituent components, which then get reduced even further, so that we can complement one another in terms of having some redundancy and backups for overall metabolic function. Being able to consume a protein, degrade it into amino acids, and then funnel amino acids into gluconeogenesis is an essential function for producing glucose in periods of the absence of carbohydrates from dietary supply. Now, also, nearly all of gluconeogenesis occurs in liver and kidneys of animals. There we go. So the major sites of gluconeogenesis are liver and kidneys, and this accounts for about 90% in the liver and about 10% in the kidneys. So glucose produced by gluconeogenesis in the liver and kidneys is released into the blood and then subsequently absorbed by the brain, heart, muscles, red blood cells, etc., to meet their metabolic needs. In addition, pyruvate and lactate produced in these tissues are then returned to the liver and kidneys as part of normal circulation to be used in gluconeogenesis. So we have a feedback cycle connecting the liver and kidneys to all the other organs which need glucose, and then byproducts from those organs that produce lactate and pyruvate as part of anaerobic metabolism feed back to the liver and kidney to remake the glucose as well. Now, what's really important is that gluconeogenesis is not simply the reverse of glycolysis. In some ways, it is the reverse of glycolysis because glucose is synthesized, not catabolized. ATP is being consumed, not produced, and NADH is oxidized to NAD+ rather than the other way around. So gluconeogenesis cannot be merely the reverse of glycolysis for two very important reasons. First, glycolysis is exergonic overall with a delta G under biological conditions of about minus 74 kilojoules per mole. So if gluconeogenesis were merely the reverse, it would be strongly endergonic process and could not occur spontaneously. So somehow the energetics of the process need to be augmented so that gluconeogenesis can proceed spontaneously. You can probably guess it's going to be through energetic coupling. Secondly, the process of glycolysis and gluconeogenesis must be regulated in a reciprocal fashion so that when glycolysis is active, gluconeogenesis is inhibited. And when gluconeogenesis is proceeding, glycolysis is turned off completely. This prevents loops where you're just wasting energy metabolically. You have to be able to pick one or the other metabolically, because if you have glucose to use as part of glycolysis, then you shouldn't be undergoing gluconeogenesis. But if you are producing glucose via gluconeogenesis, you don't want to immediately be rapidly converting it via glycolysis either. So note gluconeogenesis is not the reciprocal of glycolysis. And what are the 2 points? Firstly, it would be too endergonic. If it was simply the reverse. And 2, it needs reciprocal regulation. So we're about to go through the entirety of gluconeogenesis, and we're going to put it side by side with the glycolytic pathway. But before doing that, a few really important highlights. Gluconeogenesis, let me make a little bit of space here. Gluconeogenesis employs 4 different reactions catalyzed by 4 different enzymes for the 3 steps of glycolysis that are highly exergonic and therefore also highly regulated. So in essence, 7 of the 10 steps of glycolysis are merely reversed in gluconeogenesis. The 6 reactions between the fructose 1,6-bisphosphate and phosphoenol pyruvate are shared by the 2 pathways. And the isomerization of glucose 6-phosphate to fructose 6-phosphate is shared as well. The 3 exergonic, highly regulated reactions, the hexokinase-glucokinase reaction, the phosphofructokinase reaction, and pyruvate kinase reactions are all replaced by alternative reactions in the gluconeogenesis pathway. So, what's replaced? What's replaced is hexokinase-glucokinase, phosphofructokinase, and pyruvate kinase. And what makes these 3 similar and good points of not being used reversibly? Well, these are the 1, highly exergonic steps, and 2, therefore highly regulated. So the conversion of pyruvate to phosphoenolpyruvate that initiates gluconeogenesis is accomplished by 2 unique reactions. This is going to be the pyruvate carboxylase, tripping over my words now, pyruvate carboxylase enzyme, catalyzed in the first step, and then we'll have another step by phosphoenolpyruvate carboxykinase. We're also going to see another step from fructose 1,6-bisphosphatase and then glucose 6-phosphatase. And each of these will be replacing these 3 steps going the other direction. So let's take a look at the overall cycle, then we'll zoom in on the differences, and then we'll talk about regulation, and that will probably be enough for this particular lecture. Okay, so let's go ahead and make a little bit of room. So going from top to bottom, let's start with glycolysis. So glycolysis starts out with, I know this is a bit of a flashback, with glucose, and glucose reacts with ATP. I need to stop dragging this around here. Yielding ADP. And this gives us our initial phosphorylation on glucose 6-phosphate. And this, I'm going to keep zooming around here, reversibly becomes converted to fructose 6-phosphate, and can you remember why? Why does glucose go to fructose? Remember, we're starting to reorganize the ring structure, so we have a pseudoplane of symmetry with a 5-membered ring, so we can divide it, and the fructose 6-phosphate then undergoes a second phosphorylation, also being coupled to ATP. And we're going to get that fructose 1,6-bisphosphate. And now from the fructose 1,6-bisphosphate, we're going to divide that dual phosphorylated 5-membered ring into a pair of trioses, the glyceraldehyde 3-phosphate and the dihydroxyacetone phosphate, which then gets converted back to a second equivalent of glyceraldehyde 3-phosphate. So let's see if we can illustrate that. We'll say reversibly becomes glyceraldehyde 3-phosphate. As well as dihydroxyacetone phosphate. And of course, we go back and forth between these so that we end up with two equivalents of the glyceraldehyde 3-phosphate. And from glyceraldehyde 3-phosphate, we're going to start the second phase where we get the conversion of 1,3-bisphosphoglycerate. And this is going to give us a, oh, excuse me, don't want to have that, an equivalent of NADH. Being produced. From here, we're going to end up yielding an equivalent of ATP per 1,3-bisphosphoglycerate being converted to 3-phosphoglycerate through a dephosphorylation. So we're getting our ATP out. And we're going to yield a 3-phosphoglycerate. Then, of course, this becomes 2-phosphoglycerate. Because we need to set up our production of phosphoenolpyruvate. So we can have our last highly exergonic step going to pyruvate. And this is going to yield ATP as well. Now, pyruvate can also be reversibly converted to lactate and can also be produced by amino acids metabolically. So, zooming in here, taking a look at the whole thing, what we've done is we've just redrawn glycolysis minus the structures. And at this point, we're not looking at regulation, but just the big picture, what's happening with glycolysis going from glycolysis to pyruvate. Well, what happens now if we're going the other direction with gluconeogenesis? Well, to start gluconeogenesis, we have to start with the bottom of glycolysis, with pyruvate. And once again, pyruvate can be made from lactate or synthesized through pathways from amino acids. Now, here's where we're going to have our first two unique enzymes which are going to substitute for the final step of glycolysis. Pyruvate is going to go to oxaloacetate via pyruvate carboxylase. This is going to require an equivalent of ATP. Then from oxaloacetate is going to go to PEP, or phosphoenolpyruvate, using phosphoenolpyruvate carboxykinase. Now, let me zoom in a little bit so I can make some space because I need some room to draw here. Pyruvate will go to oxaloacetate, and this is going to involve that equivalent of ATP coming in. So, whereas in the last step of glycolysis we're producing ATP, now we're consuming ATP to get pyruvate to oxaloacetate. This is going to be done by pyruvate carboxylase. And from oxaloacetate, we're going to go to phosphoenol pyruvate. This is going to require GTP as an investment versus ATP, and it's going to be facilitated by phosphoenol pyruvate carboxykinase. So the first step, synthetically, going from pyruvate back to phosphoenol pyruvate, happens through an oxaloacetate intermediate product and requires two enzymes highly regulated to take us going back up the pathway for gluconeogenesis. And now, once we've got these two expensive steps, notice we're dealing with a reversible process, etc. These reversible processes, including the step from 3-phosphoglycerate to 1,3-bisphosphoglycerate, are reversible. So the difference is here is that we do need that ATP to be reversibly consumed to go to 1,3-bisphosphoglycerate, because we need to donate the phosphate. And then we're just moving our way up the thing. Everything's the same, stepwise. One important thing to add here is that synthetically, we can actually supplement dihydroxyacetone phosphate with glycerol synthetically. And then we have our last two steps of gluconeogenesis, which are replacing the first two steps of glycolysis. And let me zoom in a little bit, give myself some, if I can, there we go. Whereas it took ATP investment to go from fructose 6-phosphate to fructose 1,6-bisphosphate, in gluconeogenesis, we're going to consume equivalent of water and actually liberate an inorganic phosphate. And this is going to be done through fructose 1,6-bisphosphatase. And then the final step, which replaces the first step of glycolysis, is going to be very similar. Also consuming water, liberating an inorganic phosphate, and this is going to be glucose 6-phosphatase. So, zooming back out, we can now see, wow, the delay is making this hard to size. I'll work with that. We can see the big picture now, where as a glycolysis goes glucose 6-phosphate, fructose 6-phosphate, fructose 1,6-bisphosphate, etc., all the way down to pyruvate. Gluconeogenesis goes the other direction from pyruvate back to glucose, but substitutes for the three highly regulated steps here and here and here with 4 new unique steps. So we're going to spend just a little bit of energy going through a little bit more detail on what each of those unique steps are. Okay, so now that we've made a little bit of space, firstly, pyruvate carboxylase. Which happens to be a biotin-dependent enzyme. And this pyruvate carboxylase is responsible for the initiation of gluconeogenesis which involves the conversion of pyruvate to oxaloacetate. And what this looks like as an overall balanced reaction is we have our pyruvate, and we're going to add bicarbonate, an ATP, and this is going to yield oxaloacetate. Plus an ADP plus an organic phosphate. And you can see synthetically what's going on here is we're simply adding the second carboxylate functionality being donated from the bicarbonate to the pyruvate. So this reaction takes place in two discrete steps, involves ATP and bicarbonate, or substrates, and utilizes biotin as a coenzyme and acetyl-CoA as an allosteric activator. So the first part of the reaction is simply a nucleophilic substitution where the bicarbonate oxygen makes an attack. It's fairly straightforward, but I'm not going to illustrate it as part of this lecture. If you're interested in the mechanism, it's in page 723 of the textbook, and it's fairly straightforward. Important details. Pyruvate carboxylase is allosterically activated by acetyl coenzyme A. So, two particularly interesting aspects of pyruvate carboxylase reaction are: one, allosteric activation by the enzyme by acetyl-CoA derivatives, and two, compartmentalization of the reaction in the mitochondrial matrix. So activation of pyruvate carboxylase by acetyl-CoA provides an important physiological regulation. And before I elaborate on that, can you rationalize, from what we know so far, why acetyl-CoA would be important as an allosteric activator of pyruvate carboxylase and therefore initiation of gluconeogenesis? So just take a second, think on it, pause the video if you need to, and then come back. So, acetyl-CoA is the primary substrate for TCA cycle, and oxaloacetate is an important intermediate in both TCA cycle and gluconeogenesis pathways. So if levels of ATP and or acetyl-CoA are low, pyruvate is directed primarily into the TCA cycle, which eventually is going to promote the synthesis of ATP. If ATP and acetyl-CoA levels are high, pyruvate is converted to oxaloacetate and it will be consumed in gluconeogenesis. So clearly, high levels of ATP and CoA derivatives are signs that energy is abundant and the metabolites will be converted to glucose as part of gluconeogenesis, and perhaps even glycogen as a second step. If the energy cell status is low in terms of ATP and acetyl-CoA and its derivatives, pyruvate is going to be consumed by the TCA cycle to make ATP. So, rationally, being allosterically activated by acetyl-CoA is a very, very important component. Now, secondly, I mentioned compartmentalization. The second interesting feature of pyruvate carboxylase is that it's found only in the matrix of mitochondria. So, by contrast, the next enzyme in the gluconeogenic pathway, phosphoenolpyruvate carboxykinase, may be localized in the cytosol, in the mitochondria, or both. So, pyruvate is transported into the mitochondrial matrix, where it can be converted to acetyl-CoA for use in the TCA cycle, and then to citrate for fatty acid synthesis. Alternatively, it may be converted directly to oxaloacetate by pyruvate carboxylase and used in gluconeogenesis. So in tissues where phosphoenolpyruvate carboxykinase is found only in the mitochondria, oxaloacetate is converted to phosphoenolpyruvate, which is then transported to the cytosol for gluconeogenesis. However, in tissues that must convert some oxaloacetate to phosphoenolpyruvate in the cytosol, a problem arises. Oxaloacetate cannot be transported directly across the mitochondrial membrane, so instead, it first must be transformed into malate or aspartate for transfer across the mitochondrial inner membrane, which is part of the shuttle that we just talked about in the previous lecture. So, cytosolic malate and aspartate are reconverted to oxaloacetate before continuing through the gluconeogenesis route of synthesis. Now, this takes us to step 2. Let me just move us up a little bit here. So step 2 is going to be our phosphoenolpyruvate carboxykinase, or I can synthesize PEP for phosphoenolpyruvate. And the second step in this reaction is the conversion of oxaloacetate to phosphoenolpyruvate. And what that looks like is we have our oxaloacetate, which we're going to redraw with a bent structure, which makes it clear which group is leaving. And of course, this needs that GTP that we talked about earlier, and this is going to be facilitated by phosphoenolpyruvate carboxylase enzyme, and we're going to get the production of phosphoenolpyruvate with our phosphate, our double bond formed in our enol form, plus our GDP, plus our inorganic phosphate. Excuse me. We added the phosphate. There's our CO2 gone for the decarboxylation. So, production of high energy metabolites like phosphoenolpyruvate, remember, is one of our highest energy metabolites, requires energy. So the energetic requirements are handled in 2 ways here. First, the CO2 added to the pyruvate in the first step is removed in this phosphoenolpyruvate carboxykinase reaction. And the decarboxylation is a very favorable process energetically and helps drive the formation of this very high energy enol phosphate. Note the inherent metabolic logic in this pair of reactions. Pyruvate carboxylase consumes an ATP to drive a carboxylation so that the phosphoenolpyruvate carboxykinase can use the decarboxylation to facilitate the formation of the phosphoenolpyruvate. Secondly, another high-energy phosphate is consumed by the carboxykinase. So mammals and several other species use GTP in this reaction rather than ATP. The use of GTP here is equivalent to the consumption of an ATP energetically. It's just got a different nucleoside substituting for the adenosine. The substantial free energy of hydrolysis of GTP is crucial to the synthesis of phosphoenolpyruvate in this step. So overall, the delta G for the pyruvate carboxylase and phosphoenolpyruvate carboxykinase reactions under physiological conditions in the liver specifically is about negative 22.6 kilojoules per mole. So it is substantially favorable once you've coupled the consumption of an ATP and the GTP and the decarboxylation as part of the chemical logic for what drives this first sequence of events. So, to review, once phosphoenolpyruvate is formed in this way, we lean on the reversible reactions already present in glycolysis. So the phosphoglycerate mutase, phosphoglycerate kinase, glyceraldehyde 3-phosphate dehydrogenase, aldolase, triose phosphate isomerase reactions act to eventually form our fructose 1,6-bisphosphate. So we're going to skip all the way to fructose 1,6-bisphosphate and look at the third unique reaction of gluconeogenesis. And this is going to be fructose 1,6-bisphosphatase. So the hydrolysis of fructose 1,6-bisphosphate to fructose 6-phosphate is going to be going through the fructose 1,6-bisphosphatase enzyme. And what this looks like is we've got our fructose 1,6-bisphosphate. Get all of our hydrogens in here so that we're kosher. And this is going to need a water. We'll react through the fructose 1,6-bisphosphatase enzyme and give us fructose 6-phosphate plus an inorganic phosphate, because we're going to get that dephosphorylation as part of this step, going back towards our starting point. And this is going to have a delta G of about negative 16.7 kilojoules per mole. So, highly favorable. So, like all phosphate ester hydrolyses, it's thermodynamically favorable / exergonic reaction under standard conditions. Under physiological conditions, it's a little less favorable than under the standard conditions, but it's still favorable at about minus 8.6 kilojoules per mole. So fructose 1,6-bisphosphatase is an allosterically regulated enzyme. Citrate stimulates bisphosphatase activity, but fructose 2,6-bisphosphate is a potent allosteric inhibitor. AMP also inhibits the bisphosphatase, but the inhibition of AMP is enhanced by fructose 2,6-bisphosphate. So let's look at these really fast. Citrate stimulates bisphosphatase. Fructose 2,6-bisphosphate is an inhibitor, not to be confused with the 1,6. AMP also inhibits. And this inhibition of AMP is enhanced by fructose 2,6-bisphosphate. And this leads us to our final step and our fourth unique step of gluconeogenesis. Which is glucose 6-phosphatase. So the final step in the gluconeogenesis pathway is the conversion of glucose 6-phosphate to glucose by the action of glucose 6-phosphatase. So this enzyme is present in the membranes of the endoplasmic reticulum of liver and kidney cells, but it's absent completely in muscle and brain. And for this reason, gluconeogenesis is not carried out in the muscle and brain. Those tissues are very specific to the consumption of glucose, and they don't have the machinery for the manufacture of glucose. The glucose 6-phosphatase system includes the phosphatase itself and multiple transport proteins T1, T2, and T3. The glucose 6-phosphate transporter T1 takes the glucose 6-phosphate into the ER, endoplasmic reticulum, where it's hydrolyzed to glucose and phosphate, and then T2 and T3 transporters export the glucose and phosphate respectively to the cytosol, and then the glucose is exported and circulated by the GLUT2 transporter. So there's a substantial amount of physiology coupled to the discussion of the glucose 6-phosphatase enzyme and its function. But big picture stuff first, because now that we've zoomed in a little bit, it's important that we look at the big picture. It's the coupling with the hydrolysis of ATP and GTP which fundamentally drives gluconeogenesis, meaning even though it has unique steps and it utilizes a lot of reversible steps, also used in glycolysis, fundamentally, gluconeogenesis requires energy, and it's getting it from the consumption of ATP and GTP. And so the net reaction for the conversion of pyruvate all the way back to glucose looks like this. You get 2 pyruvate plus 4 ATP plus 2 NADH plus 2 protons plus 2 water, and that's going to give you glucose plus 2 ADP plus 2 phosphate plus 2 NAD plus. Oh, I'm sorry. I got that so messed up. That is the wrong example. Going back to the beginning. I think I had the first half right, but we have our 2 pyruvate plus 4 ATP. Okay, that was correct. Something did not look right here. There we go. There's our GTP. Plus our GTP. Good. Plus our NADH. Plus our protons. Man, I'm missing something here. Plus our 6 water. And that's going to yield, our glucose, our 4 ATP, become ADP. This makes so much more sense now. Our 2 GDP, our 6 phosphate, so much better. And our 2, let me make a little bit more room here, NAD. Thank goodness. And the free energy change for this is going to be about negative 37.7 kilojoules per mole. So it's the consumption of the 6 nucleoside triphosphates which really drives this process. And we'll skip the alternative explanation, because if we don't include the consumption of the ATP and the GTP, we would be a positive 74 if we were just trying to push this reversibly through glycolysis. And that would have an astonishingly low K value, meaning our equilibrium would favor the reactant side versus the product side, and you would get no meaningful synthesis of glucose from pyruvate. Now, one last point to wrap up this lecture, because when we're talking about this, it's really important to keep overall metabolism in view. Lactate formed in the muscles is recycled to glucose in the liver. So, a final point on the redistribution of lactate and glucose to the body serves to emphasize the metabolic interactions between organs. So, vigorous exercise can lead to oxygen shortage, which leads to anaerobic conditions, and the energy requirements must be met by increased levels of glycolysis. Under such conditions, glycolysis converts NAD plus to NADH, yet oxygen is unavailable for the regeneration of NAD plus via cellular respiration. So instead, large amounts of NADH are reoxidized by the reduction of pyruvate, forming lactate. The lactate produced can be transported from the muscles to the liver, where it's reoxidized by the liver lactate dehydrogenase to yield pyruvate, which is converted eventually back to glucose via gluconeogenesis. In this way, the liver shares in the metabolic stress created by vigorous exercise. It exports glucose to muscle, which produces lactate, and lactate from muscle can be processed by the liver into new glucose. And this is referred to the Cori cycle, specifically. So liver, with a typically high NAD plus to NADH ratio, readily produces more glucose than it can use, which is a really good function because its job is to make glucose and supply glucose via the catabolism of glycogen stored in glucose to the blood so it can supply muscles and brain under periods of need. Now, this is one of the reasons when you undergo vigorous anaerobic exercise, you get the buildup of lactic acid or lactate in your muscles, but it's also why you get that characteristic pump from lifting weights, because your body is pushing blood into the muscle to try to pull those metabolic products out of the muscle so it can get them to the liver to regenerate. And it's a trainable skill in athletics where people who spend a lot of time in anaerobic activities become much more efficient at recycling lactate back to glucose as a secondary recovery of energy. So people who do, say, a lot of rock climbing, wrestlers specifically, people who do CrossFit, who do a lot of repeated anaerobic high threshold activities, actually have a trainable capacity to improve their ability to recapture lactate and bring it back to the liver where it's converted back into glucose via gluconeogenesis. So that's the big picture of gluconeogenesis. We're going to pick this up with the next lecture on the regulation. You know what, man? We might fit the next two things into a single lecture because regulation probably won't take that long. Let's see. But yeah, we'll start with regulation, and then we might make pentose phosphate its own lecture, or we might just piggyback pentose phosphate onto the regulation of gluconeogenesis. So regardless, I'm going to load this video up for everyone, and then I'll be talking to you about regulation and pentose phosphate pathway shortly.